These are questions 1 to 4 of our multiple choice. Thermo multiple choice, that is. Number 1 says, what is the enthalpy change for reaction 1? Well, I think this is a Hess's law situation where we're going to have to do some reorganizing of these other ones. We may or may not need them all. And so I start with hydrazine, this N2H4. I see it in reaction 2. It's on the correct side. It has the correct stoichiometry. We don't have to do anything to reaction 2. I look at hydrogen. You remember hydrogen, if it's more than one equation, I tend to ignore it till later. NH3 is in equation 2. I think that might be it. It is on the correct side, and it does have the correct stoichiometry. So all that's looking pretty good. So maybe we could add them up and get this reaction already. Let's see. If I have these two as they are, you can see that N2 will cancel with N2. 3H2 will cancel with 3H2. And that leaves me these two, and you can see why we need reaction 3. If I'm going to get them to cancel, because I can't have them in this top equation, I need to have CH4 on the opposite side. So this one is going to have to reverse, and when I reverse it, I have to change the sign, and so it's now positive 65 kilojoules per mole. And then CH2O cancel with CH2O, CH4O cancel with that. And I do have this extra hydrogen over here, but that's okay because I needed this hydrogen up there. So I'm going to have N2H2, I'm going to have NH3, so I've got the two things on either side, and I've got the H2 that I needed there. All I have to do is add up that and these two, and I will get the answer. Number 2, they want to know, do the products or the reactants have greater bond energy in reaction 2? So I rewrote reaction 2 over here. And remember that with bond energies or bond enthalpies, typically what we'd do is we'd figure out, well, what bonds are in here? There are some NH bonds, and we'd have some number, and we'd have however many there were, and we'd have some CH bonds and some CO bonds. There'd be a whole bunch of bonds, and we'd add them up. And remember, this is the energy it takes to break bonds. And over here, we'd have to form these bonds. So we'd add up all of our CH and so on bonds over here. And then we'd take this number, the bond enthalpy of the reactants, minus the bond enthalpy of the products, and that would give us the delta H. Well, they told us the delta H was negative 37 kilojoules per mole. And so what that means is when I subtract these two, this number must have been larger than that number over there. And if that's true, then the energy of the products is higher than the energy of the reactants. Now, when you're looking through the answers, we know the products are higher in energy, so it's either got to be A or C. It definitely is not C because that is talking about entropy, not enthalpy. So the answer is A. On to number 3. Under what conditions would reaction 3 be thermodynamically favored? Well, to be thermodynamically favored, it has to have a negative delta G. Overall. Now we don't have that value, but we know that the delta H of reaction 3 is negative, which is favorable. It is exothermic. And in order for a reaction to always be spontaneous, right, then delta S would also need to be favorable. Well, we can make a prediction about delta S because we have two things coming together to make one. That is more ordered, right? And if it's more ordered, that is unfavorable for your delta S. That is negative. And so what that means is that this reaction is not always spontaneous. So we can get rid of those two, right? And because the delta S is unfavorable, we would want to lower the temperature to make it favorable. So it's only favored at low temperatures. So I get C. On to number 4. Oh, I need a pencil. On to number 4. So we've got 64 grams of CH4O. We're to decompose according to reaction 4. All right, that's reaction 4. Approximately how much energy would be released? Well, you might think the answer would be 65. That would depend on how much 64 grams is. You remember, if we have twice as many moles of CH4O, it will be double that. So we need to know how many moles of CH4O there are. Well, nicely, when you convert the 64 grams of CH4O, there's 32 grams per mole. That's really nice because that means we have 2 moles of CH4O. And if we have 2 moles of CH4O and they are only reacting 1 up here, then since we're doing 2 moles, we should get double this amount. So it should release twice as much. I think the answer is going to turn out to be D. Unless, let's see, let's make sure they aren't turning around. If that were decomposed, yes, this reaction is decomposing that. That makes sense. So I don't think they switched us on it. Is definitely releasing energy. I would say D.